Let us begin. So we had an interactive session today, but I am recording this video for those who could not follow um, all the points. What we will be doing today is continue with our discussion of expectation. The important thing to remember in the definition of expectation is that this is a general definition, which means it has a summation where values of the random variable x is any value. It is weighted by the discrete PDF, and then it is summed over all the possible values. That is one way of looking at it. But we can also have continuous random variables, and in that case the possible values will be multiplied with the continuous density, continuous PDF, and then you will have to integrate over all possible values. And in the most general case, you can have a mixed random variable which will require you to carry out both these operations. So you will have to integrate parts of it, parts of the real line. Actually, you will have to integrate the discrete density over some part of the real line and the continuous density over some part of the real line. And all this can be summarized by a single integral which uses the probability measure px. Now this px is very important to understand, that this px is not the original probability measure, it is the one induced by x. We also say x induced probability measure. So if you think about this, this applies to a differential Borel set. You know, this Borel set was when you have the subscript b, what it means without that d is you just locate x on the real line and then everything minus infinity to x, that is your bx. But now when I say dbx, it means that I am just taking this region. Yeah? This is what I mean by dbx. So now you can say that dbx essentially deals with this problem, yeah, where you are just adding the weighted sums, and here you are integrating. So what we need to replace this quantity with an easy to deal with quantity, because this is a probability measure. It requires sets, and you know we are not very comfortable with sets. We want to have something. Numerically I should get the same thing, but I need something which is a function of x. I need a point function, I don't need a set function. And to follow that, if you look at this, I start with that same probability measure applied to the differential element. So by that I mean this region. So px will apply to that. You can see this here. And by definition of CDF, because these are just two endpoints, this will simplify to the CDF at the right minus the CDF at the left, and this can be seen as a differential of the CDF. That differential of CDF must be broken down to its two parts, the discrete part, which is the PMF or the discrete PDF, and the continuous PDF must multiply the length of the interval. So we can now safely say that this this quantity which I was looking for is basically nothing else but the differential CDF. So let's move on. Now we have our simplified definition. The right side doesn't change. I still have a summation plus an integration, but this integral is now much more easy to understand. I now integrate x not with respect to a probability measure but with respect to the CDF. But this integration, remember, is not the same as this integration. Here you integrate with respect to x, and here you integrate with respect to a function. So any integral where you integrate one function, some function, with respect to another function, it is not the integral which you usually encounter in calculus. This has a special name, and it is called the Riemann I don't know, this is a strange name, integral. This name is not important. The thing which you need to remember is that this integral is very different from this integral. This integral is what you have been doing in calculus, and here it is an integral with respect to the CDF, and if you forget what it means, it simply means these two sums. So instead of writing these two every time, it will not be convenient to write these two integrals. I will just use that integral. So this is a new kind of integral. And remember, both the integrand, the thing which you are integrating, and the integrator, the function with respect to which you are integrating. Remember, this is called the integrand, and this function with respect to which you integrate is called the integrator. So the integrator and the integrand both are functions in this new definition of the expectation. Let's move on and recall something very interesting about the Bernoulli random variable. If you remember, if x is a Bernoulli random variable with probability p of success, we saw last time that if I take the expectation is a weighted sum. So Bernoulli random variable has only two values, 0, 1. I have to weight this value by its probability, which is 1 minus p, and I have to weight that value by its probability, which is p, and I get p. So p is not only the probability of success, it is also the expectation. But you also remember that the Bernoulli random variable was actually an indicator function of some event which we saw as a success. So that x which I am talking about, in this case the Bernoulli random variable, that is in fact the indicator function of some success. Now, what does this mean? That if I view this x as an indicator function, what will be the meaning of this P? This P has to be the probability of success. And what is the probability of success? So what is success? What do we mean by success? That same event A. So it means that the probability of any event can be, now I know that this P is basically the expectation of the indicator function, indicator variable, random variable. So I can express any probability, the probability of any event, as an expectation. An expectation of what? An expectation of a Bernoulli random variable, which is the indicator function of that. I think something is going on here. Let me ink to shape. Let me, yeah, so now this should be disabled. Yeah. Expectation of the indicator. So we see that things are changing. We are slowly moving away from probability towards expectation. Ultimately, we will see that every probability is an expectation, and this is just the first example. So let's move on. We now need to find a way of working out the expectation. So let me put it this way. Say I have any random variable x, and I have, because I know the distribution, so I have worked out its expectation. Now I have another random variable which has been found to be a transformation of that same random variable, and I am interested in the expectation of this new random variable. So I want to know, how is this EY connected to that EX? So how can this transformation help me relate these two expectations? So to see that, if I take any value of this variable, let's say small value x, and any value small x of the other random variable, so it must be that these two values cannot be chosen freely. Yeah, this x determines the value of y as well. Yeah? They both will correspond to. So if you want to see this, say I have the sample space and I have some sample point, and this is the point which was observed in an experiment. That point will be mapped by x to some point, call it x. So once you know this, then y cannot freely assign any value. Any value assigned by y must be g of x. Yeah? So it is dictated by g basically. So it means that these two expectations must have a connection between them. So let's move on, and typically you would start by expectation of y, and say I assume that y is discrete. So I just, for simplicity, I assume that y is discrete. So how do you start? You take summation, every possible value of y, and then you multiply by the probability at that point. So you can say probability, you either write it this way, yeah, or you can also write it this way if you want. Probability that y takes that value y. Now I don't want to do this from scratch. I want to see whether I can relate this probability. So before I talk about probability, I will start with this event, y equals y. And I want to see whether this event can be related to some event related to x. Yeah? I want to establish a connection between these two. And that is exactly what you see there. You start from that event, then you realize that y is a transformation. You don't change this value. This is fixed. And now what you see is that although y has been fixed by us, the values of x, this question I'm talking about, the value of x is not free. Only those values of x which are connected to y by this equation, which is the transformation, g is the transformation. So we will take the union of all such sets, all such sets for which g of x is y. So g actually constrains the values of x. Y fixes the values of x. Now, to visualize how this can, to see an example, I will give you two examples. In one case, g of x could be a very simple function, let's say 2x minus 1, for example. So if you set this to y, and imagine you will fix y in that equation because you fixed y. So then x must equal the solution of this equation. So it will be y plus 1 divided by 2. X cannot take any other value. So here you will have just one set. Yeah? In this case, it will just be x equal that value. Yeah? Let me write that down. Y plus 1 over 2. So to see a more complicated example and to see why we have this, why we need this union, so let me go for a more complicated function. Say the function this time, transformation is x squared. So if you set this to y, you fix y. Now x, if you solve this equation, x can either be plus y square rooted or it can be minus y square rooted. So one event you can imagine will be x equals plus this is one event, and another event that is possible is minus. Now both these events will correspond to this event. Yeah? Because we are talking about the same sample space. So if this random variable has assigned this value to some point, if our transformation is this g, then x must have assigned. So actually this also means that y has been assigned to more than one sample points. If you look at the sample points, if you look at the sample space, if there was only one point to which y has assigned a value y, then no other variable can assign two values. X would also have assigned it a single value. Now we know x has assigned two values. So it means that y must have assigned this value to more than one sample points. Even it can even be three. Yeah. So but we now know that no matter how many points do you have in a set, if all the points of that set were assigned this value by y, some of those will have been assigned this value by x and some would have been assigned this value by x, and that's why I need to take union. That is why you need this union. This union is so important. So a question and y in this case a question in y translates to a union of questions in x. And now we just bring that thing again. We are now in a position to discuss this probability, the probability of that event. The probability of that event will now be the sum of these probabilities. So union of disjoint, you apply probability. So you start with this, when you apply probability, the probability of union will be the sum of probabilities, and the sum is not free. The sum has to be respecting this condition. Now this condition automatically changes this value. Y cannot be free. Normally without any information, y could have any value in this summation, but now y has to be limited to g of x. For y there is no other possibility than the fact that it must equal g of x. So if I set y to g of x, then this summation, even if this summation is over all possible values of x, I don't mind, because here I have limited it. So what does this all tell me? That I have basically I have my result, right? Let me just, I can now remove all this, and the result I have is this: the expectation of a transformation, because y is a transformation of x, follows the same formula. You see, let me clear the canvas again, just to make sure that you know what I am talking about. When I have any variable x, what is the expectation? You take values of x, and then you, if it is discrete, you just take its discrete density, and because it's a probability for discrete case, so you just add over all possible values. Yeah. If I now replace this with g of x, what I have showed here is that I don't need to do anything. I can use the same formula, compare this result with that result. I do not, so remember this was my y. I do not need the density of y. I can use the density of x, actually discrete density, or PMF if you want. all I need is to replace that x by g of x. Now that has saved us a lot of work, because imagine if you had to do that. This is the definition of EY. You would have needed the distribution of y. We don't need the distribution of y if we know the distribution of x. So G has saved us, it has spared us from the distribution of y. Yeah, we can use the distribution of x for all the calculation. I think that means a lot if you think about this. So let's move on. If some of you are not convinced about this, because we showed it only for discrete random variable, you can think about continuous. Yeah, then the summation will be replaced by integration. But you can also think about a mixed random variable where you have both. So instead of looking for that horrible formula where you have summation as well as integration, we will use that simple integral where you take any value of x of a general random variable, whether it's continuous or discrete or mixed. You just integrate it with respect to the CDF and you get your expectation. Yeah? So if we want something like that for another random variable y, which is a transformation of x, we would need something like that. We will start values of y and we will need to integrate it with respect to the CDF of y. So we would also like to be spared of this CDF. If we know this CDF, it should be possible. So that is what we are trying to achieve here. Start with a question about y. So this is a set that y takes values around small y. So if you don't understand this, just think about a value y and imagine a short tiny region around that, and that is what we mean by the differential Borel set at y. Now that can be connected to a union of sets, similar sets on the x-axis. But instead of one, you can have multiple sets depending on this equation. If this equation gives you a unique solution, you will have just one-to-one mapping. If it has multiple solutions, you will need a union. And I can now basically work with this differential CDF, and I can attack that differential CDF, which by definition is the probability of that tiny region, which can now be expressed as a summation of that union, because the probability of union is the sum of the probability, and these individual probabilities are actually, so you see that is exactly what we obtained. The CDF of y has been obtained in terms of a summation of CDFs of x, and summation is over the solution of that equation. So that has simplified the general case as well. The expectation of this y, which is a transformation definition, usually you will need this, but if I exploit this equation, I can make use of the same formula, just replacing x with g of x and using the CDF of x. I don't need the CDF of y. This is something which you need to understand, otherwise you will not appreciate the importance of this result. So we can now put this to use. So this is now our new definition. Yeah. Actually, we can use this as our new definition, because this includes everything. The expectation of any function of x, it can be x, it can be x squared, it can be 2x, any g of x. So all I need to know, because it is a function of x, so all I need is to start with the CDF of that x, and this g must be evaluated at every point x, and then you integrate over the entire real line. That's it. Now we can try something. This g of x, you already have seen many examples. So if we think about examples, I gave you one example like that, 1 to x minus 1. Then I had given you another example, x squared. You can have many examples. What if we take the indicator of some set as an example? But this time we chose B to be a Borel set. Now what does that mean? If this were not a Borel set, if the indicator function was defined for a set A of the sample space, the original sample space, original sample space, then this indicator function turns out to be a random variable, and that's why it applies to some point omega. But this is different, because this transformation, when I say this transformation is an indicator function, what I mean by that is that it will apply to values of x, not the outcomes of the sample space. So I have some real line where I have values of a random variable, and I apply a transformation, and the indicator function now, because it's a point function, it doesn't have to be applied to sample points. It can be applied to any point, and this x is also a point. So if I apply an indicator function to x, and I check whether that x belongs to some set or not, that will give me a transformation. So it is as if I am transforming, because this x is a value of x, so it is as if I am transforming any random variable. Here this random variable was specifically Bernoulli. No matter what is A, the indicator function will always give you a Bernoulli random variable. But here, this x can be anything. X can be any random variable. All I am doing, because when I was doing these transformations, I didn't say what is x. X can be any random variable. Bernoulli, binomial, geometric. So here I can have any random variable, and as an example of G, I apply the indicator function, and I can get any random variable. What if so let's call this Y. What if I use this result for this special case? So let me use this result, the expectation of g of x, and g of x in this case is the transformation of x dictated by the indicator function. So how do we go about it? We use the same definition. Instead of g of x, I will have 1b of x, and I will have to integrate over the CDF, and this integration has to be over the entire real line. Although this integration is over the entire real line, but what does this do? This simply means that because we know this indicator function will be 1 only when x belongs to b. So although x goes from minus infinity to plus infinity, in general, this multiplication inside will ensure that without this, the integral of basically 1 over the CDF, will actually be limited to B. Yeah, it cannot be free. And you think about this, what is that? That is simply because your df is a change of probability and you are integrating it over a set, Borel set, so that will simply be the probability of the Borel set. Remember, the probability must be calculated according to this measure. So if you, yeah, that is what we have done there here. The expectation of the transformation obtained by an indicator function, let me repeat, applied to any random variable, any general random variable, can be shown to be equal to the probability of that Borel set under the x-induced random variable. You can compare it with our previous example when x was an indicator function that was a random variable, not a transformation, and when you took the expectation, that was simply the probability of A. This probability was not x, this was the original events, you just took the original probability measure. Here you take the induced, yeah, the probability measure induced by x, and you apply it to B, and you see B as a Borel set of the real line. So B is a subset of the real line. Yeah? B is a subset of the real line, and A is a subset of your original sample space. Whether you look at this result or at that result, one thing is clear. Let me summarize it there. That the probability of any event, and let me just write PROB. This PROB can be P, the original, or the induced, or it can even be another random variable, don't mind. All these probabilities, whichever domain you are using, they can be expressed as expectations, and expectations of some indicator function. That indicator function will in some cases be a Bernoulli random variable if we are talking about this measure, or it will be another indicator function which arises as a transformation. But one thing is true in all cases, that probabilities can be replaced with expectations. So now I can show you, actually I can prepare you. This is just an yeah, I already discussed it on this right side. So I just want you to notice this thing, that from now onward our language will change. Yeah. So remember, in the first part of this course we were dealing with sets, then we moved from sets to random variables, and we were still dealing with probabilities. Yeah, because the probability of the original sets like P of A, and then when we switched to random variables, we replaced that P with this Px, and then we had sets, Borel sets, and now we are replacing both this P and Px. So both P and Px are being replaced with expectation. And one more thing, expectation is an integral over the CDF. So this integral will be a summation or the usual integral. In any case, this integration will be linear. So which means that we don't even need to prove the linearity of expectation. It just borrows linearity from integration and from summation. So if somebody asks you why is expectation linear, You have to tell him, okay, I know it's linear because integration is linear and because summation is linear. I don't need to prove it. If you want, actually, this is not a proof, this is just a statement. I just start with a random variable x and I multiply it with a constant. I add a constant to this, and because this is linear, this can be applied to them individually, and we know this is the expectation of a deterministic quantity, so that must not change, there is no uncertainty. And we can also think about special cases. Yeah. Special case with a equal 1 and b equals minus the mean, we can show that the expectation of the difference between a random variable x and its own mean will simply be 0. So that is pretty standard. And you can, if you want, you can apply it to the 2-point distribution where you know the expectation of Bernoulli random variable and you want to use the transformation to work out the expectation of a 2-point distribution. You can do this yourself. I will only comment on the result. You know, there are only two possible values, a and b. A is weighted by the probability of success, B is weighted by the probability of failure. So it means that you got it right. Although we never used the definition of EY directly, we used transformation and linearity. Same can be applied to discrete uniform. The discrete uniform distribution with n points going from 1 up to n, all having the same probability 1 over n. If you remember, the expectation was, or the expected value to be very precise, was n plus 1 over 2. Now that n must be replaced with b and that 1 must be replaced with a, and you should get a plus b over 2. That is something which you can show by using transformations. Yeah, I can use the transformation. So this is my g of x needed to go from the standard uniform to this general uniform. Apply the transformation and you get that exact same result. Now we need to ask something. Let me go back and let me clear all the annotations here as well. When we talked about the linearity of expectation, we just phrased it in a function of x. So for g of x, we took a linear function. But why didn't we try something like that? This is what you do in signals in a system, where you take two signals and you apply it to the same system, and then you see what happens. So I can ask this question: if x is a random variable, and if I know its expectation, if y is another random variable and I know its expectation, what if I take their linear combination? So if E is linear, I should get A times EX plus B times EY. This should have been very standard. Why did we not try that? This looks very easy, but this is complicated. To see the complication, let's call this Z. So let me call this Z. So what will be EZ? And let's say that X, Y, and Z all are discrete for simplicity. So you will start with, if you go with the standard definition, you will have to sum all values of Z by weighting them yeah, by the respective probabilities and overall possible values. And this is your combined joint. This is the PDF of Z. Now remember, when we had a single function of a single random variable, we saw that we could simply write Px there, yeah, or F, we can even write the discrete density, and then we multiplied it by Gx. Now we can't do this here because this probability, if you remember the bit transmission example, this probability depends on two random variables. So we need, whether we talk about PDF or CDF, remember the general uh, quantity is CDF. We need a CDF or PDF of both X and Y if we want to relate this quantity with quantities associated. So let me put it this way. What I actually need to do is that I will have one random variable X and I will have its probability measure. I will also have its CDF and I could also have its PDF. I will have similarly another random variable with its own probability measure, with its own CDF and with its own PDF. Now if I have a third random variable which is a linear combination of these two, yeah, or any, basically any function of X and Y for that matter, I will need, of course, if I did not want to connect this with X and Y, I would simply say, okay, I know Z and I could have its measure and I could have its CDF and I could have its PDF, but I cannot connect these quantities with those quantities if I don't talk about what is called a joint distribution. In joint distribution, I will need a probability measure which is induced by both X and Y, and that could look like the probability that X belongs to something and Y belongs to something. That will give me this joint measure. So unless we do that, we cannot ask that question of linearity. It was not easy, but it's not difficult either. Joint probability distributions can be discussed by asking questions like that about two random variables. Let's say X equals X, Y equals Y. Yeah, you can ask any question like that in case effectively your Borel set must be. So remember, when we were dealing with single random variables, the Borel set was a subset of the real line. Now our Borel set will have one real line for X, one real line for Y, and the Borel set will be some set of this region. Let's say this is a Borel set B. Now, so X and Y can be said to take values from some Borel set. And in that case, the inverse has to be for the pair. You cannot say X. So for example, if I want to know this Borel set, the pre-image of this is my original sample space, and I want to know, oh, tell me where this came from. Now you cannot say X inverse of that and Y inverse of that, because this B is a result of both X and Y. So the best you could say that, okay, let's make a pair of X and Y, and that pair will apply as an inverse function on B, and this will give me the actual event of the sample space. So remember, all sample points of the sample space to which x and y have jointly assigned a value, a pair basically, a pair which belongs to B, Yeah, that is what we mean by the pre-image. So it means that the Borel set, so normally for single, when we talk about CDF of a single variable, we just choose a point B and we define a special Borel set there. Now we have to choose a point xy and we have to define a region to the left of that and to the below that. This region will be called bx comma y, which is bx cross by. Yeah, this bx, this by, and just cross it, and you can see it. Bx, everything to the left of x inclusive, everything below y inclusive. Take the cross product, and if you want the pre-image, that will be like x cannot exceed small x, y cannot exceed small y. If we now apply probability to this, and of course there the probability will be px comma y, these two will give me the CDF, the joint CDF, and that will be denoted by f x comma y of xy. So you will see it on the next page. Yeah. So generally the probability measure will take this form. It will be a joint measure applied to a set B which lies in a plane. Yeah, and if I take the special Borel sets, yeah, those Borel sets which I just pointed out, any point and everything to the left and to the bottom is that special Borel set. Yeah, you can confirm it there, and that is what you mean by a joint CDF. Yeah. And you can also think about the differential. Why we need differential? You can think about this yourself. Just take a tiny region around x, take a tiny region around y, take the probability, and that will give you a differential CDF, joint CDF. We use d squared because it has two differentials. Yeah? It's like in multivariable calculus, if you have a double integral, so you either say dx dy, but here we have a single notation b for the Borel set. So if you remember, if you want to represent this by a single quantity, that this d squared will remind us that, okay, I'm taking the differential of a Borel set B, and d squared will remind me that actually it is actually a cross product. Now you can also wonder, how can we go from the joint CDF? Let's say I have the joint CDF. Yeah. Can I recover from this the one-dimensional CDFs? And the answer is yes, because if I want to recover the one-dimensional CDF of x, I just have to ignore y. I don't care what is y. So y can take any value on the real line, which means that I can cross bx with the full real line on the y-axis, which means that the question will only be about x, and I don't care. Y can take any value from minus infinity to any other point, and that will give me the one-dimensional CDF. Same can be applied there. I only care about by, I don't care about x, and that's why I replace When I replace x with the real line, I don't care about x. When I replace y with the real line, I don't care about y. And then you get the one-dimensional CDF. And whenever the context has a joint CDF, these one-dimensional CDFs are also called marginal CDFs. It's like a table margin. Yeah, you have a table, 2D table, and this is one margin and that is one margin. It's just a standard name. And if you remember, whenever we talk about joint probabilities, joint means intersection. So you remember we had this question in probability that if the intersection, if the probability of an intersection is the product of their probabilities, we say that the two events are independent. Now you know this joint CDF is also a probability. So if it is the product of the one-dimensional CDFs or marginal CDFs, we will say that x and y are independent. So this is the independent of events, and that will be the independent of random variables. So when we say two random variables are independent, what we mean by that is that their CDFs are simply, the joint CDF will be a product of the marginal or one-dimensional CDFs. Now this discussion should be stopped here because we don't want to get into joint CDF at this point. This was only needed for this definition. Remember, this was our standard definition. In one-dimensional case, any transformation applied to x, take the integral over the entire line of g of x, and the integration must be with respect to the one-dimensional CDF. I just need to replace this one-dimensional CDF with the joint CDF, this g of x with a function of two variables. I will definitely have a double integral, and I can now define the expectation of a function of two variables. So that means that now I can ask questions about linearity, that if this g of x is a linear function, I can now say what will be its expectation. I will simply apply this result, and because double integral is a linear operation, yeah, this will be a double summation or a double integration, or maybe one summation, one integration, because it can be a very complicated scenario. But this general definition will always have two integrals. So because summation, integration, they're all linear, so this must be linear. There's actually nothing to prove here. We can just state this. But for this statement to make sense, we needed to understand the joint distribution, joint CDF, joint PDF, joint density, and so on. And we can also do something similar if the transformation is an indicator function. Remember, this D is in 2D, so this has to apply to a point in 2D. And if we apply that same result, it can be shown to be the probability of a Borel set. So the probability of any Borel set can be expressed as an expectation, but this is nothing new. We already know that. Actually, we were expecting that. So now we can state the linearity of expectation. That was it for today. Next time we will start with the spread of a distribution. So when we say mean is only the location. A distribution is located somewhere, either the peak or some other value. But spread tells me how wide the distribution is. So let's wait for the next lecture for a full-fledged discussion of the spread of a distribution. Bye for now.